So now I'm going to give you the 5-minute introduction to where particle physics came from, just to give you an idea of, first of all, what are these particles we talk about in particle physics, and what are these accelerators and detectors that we use to study them. You can start this story sort of anywhere, but one way to start it is with cosmic rays. There are cosmic accelerators that accelerate particles to very high energies, and these high energy particles hit the atmosphere. They have been since the beginning of time, and early on in this century, people went up in balloons to try and study what was happening with these cosmic rays hitting the atmosphere of the Earth. And when people started to get the ability to detect these particles, immediately this whole sort of zoo of particles started to develop. There's particles like the proton and electron that we're made out of. There's particles like the photon that have to do with forces. And then as they started to study these, they almost immediately discovered new particles that they didn't really have any explanation for or any sort of neat way of fitting them in to our ideas about physics. And the first two examples of this are particles called the pion and the muon. And these are were first seen in these cosmic rays hitting the Earth. Again, as I mentioned, we don't actually know, we can't see that anyway. We still don't actually know where these cosmic accelerators, what exactly they are, where they come from, and that's really a mystery for astrophysics to solve for us. We developed early on these, what we now consider primitive techniques to detect these particles. Here's an example of a cloud chamber, this old-fashioned way of detecting charged particles like the positron, that's the antiparticle of the electrons. And here's another old-fashioned technique. This is just actually photographic emulsion. And you start to see not only that there are these weird particles, but that particles decay into other particles. So here's a simple example of that from the discovery of the pion. Here is a track here which actually represents this new particle, the pion, the charged particle. It decays, it makes a new particle, and this particle is another weird particle called the muon. And the muon also decays after some period of time into an ordinary particle, the electron. And not only that, but if you look at these tracks, you see that there's sort of something wrong here with conservation of momentum, right? There was momentum here, and then this guy changed direction. So what was going on there? Well, we now know that what was going on there is that every time you had one of these decays, there wasn't just this particle produced, there was another particle that you didn't see. This we now know are the neutrinos, which are particles that are much more difficult to see than these other particles. So I wrote them as dotted lines. So this is particle physics as they did it in the old days, in the late 40s, let's say. And they had the technology to see some particles they couldn't see, and they started to see these patterns of particles decaying into other particles, but they didn't really know what was going on. They didn't know what a pion was really, why it was there, what a muon really was for, and it was all a little confusing. Almost immediately in the late 40s, early 50s, things got more and more complicated, and particle physics for a long time became a real mess. This is just an example. A whole bunch of new particles were discovered called strange particles. Again, they had no idea what these particles were. They were unstable particles that decayed to other kinds of particles. People, invented names for them, but they didn't really know what it was all about. So some of these particles which decayed to protons, they called hyperons. Other ones decayed to pions, so they gave them a different name. They called them kaons. But they didn't know what these things were. And if you look at a timeline of the discovery of, so this is a timeline and each particle and when it was discovered, you see that, well, okay, for a while here, there were a few weird things. This is the muon and the pion that I mentioned. And then all of a sudden, you start to see particles, all these particles discovered. Nobody knows what it's all about. They almost literally ran out of Greek letters to represent these things. And particle physics by the mid-60s is just like a big confusing mess, and nobody knows what it all means. So we studied these guys in detail, and then we actually figured out what was going on here, this whole big mess. This whole big mess doesn't bother us anymore. Most of these new particles that were discovered are what are called hadrons, and we now understand that the reason there's so many of them and the reason it's so complicated is because those particles aren't elementary particles. They're made out of other kinds of particles, called quarks. So this is one of the big insights that was made by studying particles in detail in accelerators. And the patterns, it's the usual kind of thing. You start with simple ingredients, and out of that you build up complicated patterns. So for example, the ordinary stuff, that we're made out of, protons and neutrons, is made out of up quarks and down quarks, two kinds of quarks. A proton is two up quarks and a down quark. A neutron is an up quark and two down quarks. And that's what all ordinary protons and neutrons and thus all ordinary nuclei of all ordinary matter is made out of, those two quarks and those combinations. And these weird particles, the strange particles that they were making, the reason they were strange, it turned out, is because they were made out of a new kind of quark, a third quark called the strange quark. And that was the only difference. The only difference between the proton and the neutron and all these other weird particles they were making is that some of these particles had one strange quark instead of no strange quarks, and some of them had two strange quarks, and some of them had three strange quarks. And the other difference is that here all these particles were made out of three quarks at a time. There are also hadrons that are made out of two quarks at a time. For example, the pion, that first weird particle I showed you, is made out of a quark and an antiquark. So once you realize that these things are quarks and you understand some of the physics that's holding these quarks together, there's a force called the strong force that holds these quarks together to make these other particles. Then you start to see the regularities and all this complicated stuff you didn't understand, all boom, all of a sudden, you make sense out of it. And at the end of the day, you start to forget about all this complicated stuff and you start to focus on the quarks themselves. And you say, well, okay, really what I'm interested in are these elementary particles, I guess, these quarks. And now I want to know how many quarks are there altogether. There's two in ordinary matter, but there's at least one more that I showed you there. So how many are there altogether? And what are their properties? What are the forces between them, and what do they like to do? And one of the weird things that we now know about quarks is that you actually never see a quark by itself. You can see these combinations of two quarks or three quarks, but you never see one quark. And the reason has to do with the forces by which quarks interact. Quarks interact through what's called the strong force. The reason it's called the strong force is because it's strong. And because of that, when you try to rip two quarks apart, what happens is that instead of ripping them apart, what you do is you make a really big tube of energy between them. And as you try and pull them farther and farther apart, all that happens is that tube of energy gets bigger and bigger, has more and more energy in it. And then eventually what happens is that energy starts to produce new particles, including new quarks. And so instead of getting a quark all by itself, what you get is a bunch of these hadrons. You actually produce more quarks out of the energy between the force between the two quarks, and you make hadrons instead of making just a single quark. So nowadays in particle physics, when we talk about looking for quarks, we never see a quark by itself. What we see, generally speaking, when we produce a high energy quark is just a whole bunch of these hadrons, a whole bunch of these pions, those other particles we showed you on that chart before. And the way you count quarks is essentially by counting groups of these particles, these hadron particles. If I produce a high energy quark, that then tends to produce what's called a jet. It's just sort of a spray of these hadron particles. And the fact that they're all more or less going in the same direction is because originally they came from a single high energy quark. So you count quarks to some approximation by counting these jets, these sprays of particles. And that's words, but this is what it looks like. So here's the actual pictures from the detector, and you see here, each of these lines represents one of these particles that I can see, one of these hadrons. And you see a bunch of lines going this way, a bunch of lines going that way. These blobs actually represent energy. Another way of looking for particles is counting where energy gets deposited in your detector. And you can see here visually that it looked like I produced two jets, two of these sprays of particles. And what we think is happening there is that I produced a high energy quark that went this way and another high energy quark that went that way. And that's what produced these two jets of particles. So this is how you see quarks. You don't actually see the quark, but you see these jets of particles produced by quarks. This is the same thing, but just looking at where energy is deposited in your detector, and you see that there's two big spikes here, and those two big spikes come from all these particles, each of which we think was produced by a quark. So this is now much more sophisticated. You know, that first picture, that photographic emulsion of a pion going to a muon, that was very primitive, simple stuff compared to what we're doing today. And part of the complexity of what we do today is that we're not just looking at simple particles like muons and electrons, but we're looking at complicated processes involving quarks that produce these messy sprays of particles. So let me give you the big picture. The big picture is, it's simple to say in words. There's a big universe out there. It's made out of matter particles. These matter particles, we call them fermions. They have a certain weird property that I'll discuss in a minute. Those matter particles are either quarks, as I was just saying, or what are called leptons. The electron is the simplest example of a lepton, but that particle I call the muon is also a lepton. So these are particles that I can see all by themselves. An electron, I can pull it out and look at it all by itself. So they interact with different kinds of forces than the quarks do. And that's it. All matter, including unstable matter that we produce in the laboratory, everything that we've been able to see or produce in the laboratory that's matter is made out of quarks and leptons. Then there are forces, and forces in particle physics are also carried by particles, force particles called bosons. And there are different kinds of force particles. The photon is the one that everybody's heard of. But there are also the particles that carry this force that holds quarks together. And there are other kinds of force particles. Here I've separated out one of them. The graviton is what we think is the force particle that carries gravity. And the way we do particle physics is we talk about some of these particles. You take your pick, some particle you're interested in, like a quark. And now maybe I want to know, how does a quark interact with some other particle, like an electron? And we look at that in the laboratory, and then we try to match that up with the calculation. And nowadays, in most cases, we do that using what are called Feynman diagrams, which is first of all a picture of something happening. So here's a picture of a quark interacting with an electron. And the way it's interacting is through a photon. So what I'm looking at here is the electromagnetic interaction of these two charged particles, a quark and electron. And the way they interact can be described with a photon. But Feynman diagrams are not just a picture. Each of the pieces of this picture actually stand for part of a calculation. So this is a picture which stands for a calculation you can do, which actually tells you in detail how in this case, a quark and an electron interact through the electromagnetic force. So it's not just a question of naming particles and drawing pictures. It's a question of being able to do precise calculations that tell you how these things interact. So that's as much detail as I want to get into there, but I don't want to make it seem that simple. There are weird things and complicated things going on here, and I don't want to sweep it all under the rug. As far as we know, all of these interactions of all the particles obey the laws of quantum mechanics, which are very complicated and weird, and they also obey the laws of special relativity as formulated by Einstein. And because of that, it's quite complicated in many cases to describe what's going on here. And in fact, even some of this terminology is a little misleading. In quantum mechanics, particles sometimes are particles, but sometimes they aren't particles, and things get very weird. I'm just going to give you one example of that. I mentioned that matter particles, the things we're made out of, are called fermions, and those are different from force particles, which are called bosons. And you might ask what fundamentally is different about them, other than the fact that one is matter and one isn't. And in quantum mechanics, what you find out is that the bosons, when you describe them, have the sort of simple properties that ordinary objects have. For example, if I take this cup and I turn it around 360 degrees, it's back where it was again. Sort of an obvious property of ordinary objects, right? Well, bosons are like that, but fermions aren't like that. If I take a fermion is more like this. I take it around 360 degrees, I'm not back to where I started from. That's the way fermions behave. But if I take them around again twice, then they do go back to where they start from. Now, for ordinary objects, there's no real way of making sense of that, but that's the way fermions are, and that's actually the fundamental properties that make fermions good for matter and the bosons good for forces really have to do with that weird property. So there's a lot going on here that I can't explain in detail, but it's fundamental to why matter is matter and why forces are forces. That was my demo. So, there's a lot of work there. There's 50 years of both doing experiments and wrestling with all these theoretical ideas. And in the end, you get a model. And the idea of the model is that you want a precise description of first of all, what all is there, and then how all of it interacts. And we think now that for all of these matter particles I was talking about, and for all of the forces except gravity, we actually do have a model which we think precisely describes all the behavior that we've seen in experiments so far. And I just wanted to call out here that the one exception is gravity, for which we don't have a modern theory. In fact, the best theory we have for gravity still is Einstein's general relativity, which he developed in 1915. That theory is actually a classical theory. It doesn't know anything about quantum mechanics, and there's something wrong there. There's something we don't understand fundamentally about gravity, as I'll mention again later on. For the kind of particle physics that we usually do, the fact that we have a lousy theory for gravity actually doesn't matter, and the reason it doesn't matter is because gravity effects are very weak compared to the rest of the forces of nature. And so if I'm looking at an electron interacting with a quark, they interact via gravity, but it's such a small effect that we can ignore it without really having a good theory of gravity. So, of course, this model that we developed is called the Standard Model. What it is it's basically a list of particles with some of their properties, like their charges. It's some numbers that tell you things like the strength of the various forces. And then it's some mathematical formulas that tell you how these particles interact in terms of these forces. And those mathematical formulas are actually extremely concise. You could literally write them down. All of the mathematical formulas you need to understand all of the interactions of all of the known particles, at least in principle, can be literally written down on a napkin. So just to go through that, here's all the particles that we know about. There's these leptons, which is the electron, the muon, the tau. The neutrinos go along with those guys. There's the quarks that I talked about. So the answer to the question of how many quarks are there is there appear to be 6 quarks. There's the up and down quarks. That's what ordinary stuff is made out of. The strange quark, which I mentioned, the charm quark, the bottom quark, and the top quark, the one that was discovered here recently. And here are all the force particles we know about. There's the photons. There are 8 particles called gluons, and these are the particles responsible for holding quarks together. These are the guys that make quarks stick together. That's why we call them gluons. That's why quarks can't be pulled apart. And then there are these other 3 particles called the W and Z bosons. These are responsible for what's called the weak interaction. I'll show you in a second why that's interesting. There's the graviton for gravity, and then there's this other weird boson called the Higgs that we actually haven't discovered yet, but we think is there, and we're looking for it. This is not the entire equation you have to write down on the napkin, but it's about 2/3 of it, written in Chris Quigg's excellent handwriting. And of course, each of these things stands for something, and it also stands for a whole procedure involving quantum mechanics and special relativity that you have to know to extract information from this. But this encodes all of the interactions that we know about. So, okay, you've got your standard model. It's a wonderful, precise theory. What can you do with it? Well, again, it's supposed to explain all of the fundamental interactions between elementary particles via all of the known forces. So it explains, for example, the structure of matter. This happens to be the inside of Ken Lay's head, but it could be any ordinary matter. And this is the story you already know, right? There's atoms, and inside the atoms there are these electrons, and then there's a nucleus. There's protons and neutrons inside there, and each of those, as I told you, is made out of either 2 up quarks and a down quark, or 2 down quarks and an up quark. So we understand the structure of ordinary matter, and we also understand the structure of lots of weird kinds of matter that we make in the laboratory. What else does the Standard Model explain? It explains how the sun shines. There's a lot of complicated reactions for the sun, but the first one that takes place is 2 protons. So the sun's a big ball of hydrogen, right? It's a big hot ball of hydrogen. So how does it produce energy? Well, the thing that gets everything going is that hydrogen is basically protons. 2 protons every once in a while can get together, and through an interaction, which I'll explain over here, one of the protons becomes a neutron, and that's a kind of nuclear fusion process, and that nuclear fusion is what powers the sun. That process, if you look at it at the fundamental level, what's going on here, this proton turning into a neutron, is one of the quarks, one of the up quarks inside the proton is turning into a down quark, this other kind of ordinary quark that we're made out of. And via an interaction that involves this W boson, that was this weak interaction force that I mentioned that didn't seem to be good for anything. It is good for something. It's what makes the sun shine.